Okay, good afternoon, everyone. Okay, yeah. Welcome to the reality. Wake up, wake up. Okay, anyway. Yesterday we finished the directional derivative. So, if you look back to the calculus 1, there are some similar concepts in our course for calculus 2. So if you see that we now have more than one variable, right? So if we talked about derivatives, then we are talking the derivatives not only in a single variable x, but also in more than one variable. So simply to say that because of the multivariable, then we have, for example, last part we have the chain rule, which we are introduced by this diagram, and I hope everyone can try to familiarize with this method to find the partial derivatives. And then also we've introduced by this implicit method, basically similar to what we have in calculus 1, but the difference is we can have two variable or three variable inside. And then another point of view that we've just introduced yesterday is the directional derivatives. So basically, directional derivatives is so if you remember, in calculus 1 we've introduced the tangent line to see the slope, right? To see the slope, whether it's increasing, decreasing, okay? And then we have also the second derivative, which we are having concavities, right? Whether the curve is like this or this, right? And now we have the directional derivative, which this is basically saying that the rate of change of the tangent plane, okay, in some direction. Okay. The direction we call the unit vector u, okay, within this directional derivative. So simply we say, let me just get to the conclusion here. Simply we say the directional derivative, okay, is a gradient factor. The gradient factor is factor that compose of the partial x and partial y. Partial x and partial y is our tangent line in tangent plane. Okay. So we have a tangent plane right now because in the 3 dimension, and the tangent plane, if you remember, it's composed of two lines, right? Two lines that we've connected together at some point. And those lines has a slope that is partial x and partial y. Okay. And we call this factor the gradient factor. Okay. And this u is our direction. Okay. So if we want to know how much the dz or the z-axis change with respect to these directions, then this is our approach. Okay, so we can make a dot product between the gradient factor and the unit factor u. Okay, now suppose we have some example here. Let me give you. So before we move here, let me give you some example before going through the next part. So here's the example. So let's say we have a function that is 3 variable. Now what happens if we have 3 variables? The directional derivative also apply, which means we have partial x, partial y, and partial z. Okay. So first, if we want to find the gradient factor of f, so simply this is going to be, let me write, partial x, partial y, and partial z. So which means that we are going to derive with respect to x, with respect to y, and with respect to z partially. So partial x, we just derive x, which is just x, and then sine yz is a constant, so we just have sine yz. Okay, and in partial y, then we are going to derive yz inside this sine yz, which in turns it's going to be, and having a chain rule, so yz becomes z, so z, so this will be xz, and then cosine yz, right? Okay. We write here dy, or not dy, it should be partial. Okay, just to make sure. So we take, this is become cosine yz, and then we still have the dy, that is yz, right? Chain rule. Oh, sorry, x. So this becomes this, right? Okay, so let me erase this. Hopefully you're familiar with the partial method. Okay. And then partial z, then we can take x, y, cosine yz. Okay, that's it, the gradient factor. Okay, now another questions. This is I think a typical direct questions. We have the functions, and usually we have the direction, and you just put into the operators and then just compute the results, and then find directional derivative at point 130 in direction, let's say direction v, I plus 2j minus k. Okay, now what you need to remember that this is just a regular factor, which means that we need to make it into unit factor first. Okay, so let me write maybe here that we have the directional derivative is equal this, right? This u is unit factor. Okay. One thing that perhaps important to note. So every time you see the factor that being a direction of this directional derivative, then we need to apply this unit factor first. Okay, so then we need to find the unit factor. Let's say u is just defined by the magnitude value, right? Okay. So it's 1 plus 4, 5 plus 1, 6, right? So it's square root of 6, yes. So this is going to be, let me just write directly with this bracket. I forgot the name of the bracket, but I remember the name when I type into a function. You see I write /Langle or wrangle for the right one. So this will be 1. And then this will be -1 and square root of 6. Okay, that's the unit factor. Then we apply this unit factor into our dot product. So, if you want, we can start first from the gradient factor. We can find the gradient factor at the point 1, 3, 0. So 0 for z, so this will be 0, right? 0. And then this is also 0. And then this will be 1, right? This will be 1 or wait, 3, because y is 3. So this is the gradient factor. So the directional derivative at this point is basically the dot product from 0, 0, 3 and the unit factor. Of course, the result will be just a scalar number, right? Just a scalar. So this will be equal to -3 square root of 6, or we multiply with square root of 6 is half, right? And another note, I think it is also maybe important to have. So whenever you have the unit vector, any unit vector from any point, for example this one, let's say this is our u, suppose, okay. And if we can define this u with some, let's say, angle, for example here we have angle there, this is any point, let's say x0, y0, then we can apply that the component for this unit vector is supposed to be sine theta and cosine theta, right? Because unit vectors totally should be equal to 1 the magnitude, right? So this is just a note. Okay, suppose that this is going to imply with some practice or exercise. So, for example, if you want to, perhaps the question is asked, you have the functions, and it's mentioned that there is a unit vector that has the it has the given angle, maybe pi over 2 or maybe pi over 3 or maybe pi over 6. It means that you can define this unit vector in terms of cosine theta or sine theta for x and y axis. It means that you can write u within this cosine theta and sine theta. This can also make sense for this one. Okay. Right. So here, I think I haven't write officially. So within this example, we can write that 3 variables also possible. And this gradient f for 3 variables, you can write partial x, partial y, partial z. And then plug in the number x, y, z. Okay. Right here, make a line. Okay, next is, if we look at this graph, let me write the title first. This is going to be the tangent plane. Okay. So tangent plane to level surface. Okay, now from the knowledge we have from the gradient factor, if you see this graph, so this is our tangent plane. Okay. So if you place a point here, point P, okay, then suppose that this is the tangent, okay, the slope. Okay. Now the gradient factor is actually the normal, right? So let me write here the gradient factor f is perpendicular to tangent factor r prime t0, let's say, for any curve that on this surface that pass through the point P. So if the gradient factor is not 0, then I think we can define this as a normal. Okay. So we can define the tangent plane So tangent plane to level surface, which is equaling some constant at point P, is the plane that pass through P and has normal vector, or maybe right here, has normal vector is equal gradient vector at x0, y0, z0. So by doing that, then we can write these formulations. So this is actually just a conclusion from the tangent plane that we already learned and the gradient factor. Okay. So the gradient factor, because that is composed from all the partial, right, from x, y, z. So we can say that those partial, in terms of the plane, is actually our normal line. Okay. So remember that this is actually the same relation if you remember the tangent plane before, right? So this is the partial, which is considered on the slope, right? And this is the point that we observe. Okay. And then, if you remember, we can also rewrite this in symmetric equations. So let me write this here. So we can write another way to write on. Okay. And I think that is finished for the directional derivative and gradient vector. And you could also see this equaling 0 for the plane here, which means that we can, because it's perpendicular, what's this? Because it's perpendicular, so we can also see that this is actually just proving that this equaling to 0, which means the angle is pi over 2. Okay? This angle here. And then put down. And what if? Okay, what if? The next question, if we have this general equation, right? So another, notes that interesting is what if S in form of z function of xy, just two variables. Now we can force this function inside our three variable equations. So we can take our three variable, like with capital F, okay, so this is x, y, z, and we can name that z is fxy, and this will be minus z. Okay. And thus this going to be, if we make out the gradient vector, then we can take this partial x, partial y, and negative 1, and we can still using the same structure. Okay. So this is I think a conclusion that you can finally using this formula for all the difficulty levels. So from the first one, we have the tangent plane and so on, right? We have from the finding the tangent and then taking it into the tangent plane, right? But now this formula we can use it for every possible case. Okay? If for example, if the case is having these two variables like this, we can just plug in and make out that we can assume that we have another function for three variables and make it into this fxy minus z, and then we can simply take out the partial and using this partial inside this. So you can just change the partial z to negative 1. And it will be the same thing as we did before, the same result. So you can do this for every, so this is maybe to simplify your process. You can just go to this, and this is going to be for all possible cases. But still, the previous method, you can still also use it, okay? But it has some limitations. Okay? If it's become more and more like having three variables like this, then you need to go to this one. But this one you can also use for the previous one that we've learned before. Okay? You can directly use, and then just using this function. So simply we can take the tangent plane. If we take this one, so partial x plus partial y and minus z minus c0. And this is becoming our normal in the linear approximation, right? It's similar. So we can say that this is equal 0, right? So we can also say this is z, z0 plus partial x minus x0 plus partial y minus y0. And this is also related to our linear approximation that we've learned before, right? Okay, so the same, right? The same as we learned before. Okay. Okay. So that's my suggestion. I give you the tips. You can just using this for all questions for tangent plane. Why I didn't give this at the beginning? Because I want to give you the process. That's the most important one, the process. Okay? The thinking process is important. Okay, so directional derivative, tangent plane to level surface, finish. But we still have struggle with that gradient factor, but after another section. So let me write here, if line, and for new sections, let me write the title first, so you can still write the notes. This is max and min values. Okay. Oh, it's too. Let me make it smaller. Okay. Okay, now the next one is the maximum minimum values. I think you can read this one on your own, but this is just to say that similar to calculus 1, we have absolute maximum, absolute minimum, we have local maximum, local minimum. As long as we know how the curve or the surface behave. Like for example here, we call this local maximum because it has, like in calculus 1, remember that you have the positive slope and then zero and then negative slope, right? This is also similar, but we look at in a surface, so we are getting the tangent plane, right? The direction seems to change after some point, and that's going to be, we say it's maximum or we say minimum. Okay. And the most that has maximum, we say absolute, or the most that has the minimum, we say the absolute minimum. Okay. And this is just some notations for the function. You put some point AB and you want to determine whether AB is minimum or maximum. Okay. Now we move to the theorem. It's similar to what we have in calculus 1. So if we have a local maximum or minimum at some point, in this case point AB, and the first partial derivative exists, then we say the partial x at AB or partial y at AB, that will be equal to 0. And the point AB, this is called critical point, or stationary in another case, but usually we say this is critical point if partial x at AB is equal to 0 and partial y at AB is equal to 0. But remember, not all critical points is related to maximum or minimum. Okay, the case for that case that I mentioned, that not all critical points giving maximum or minimum, is this one here, which we have learned in the quadratic surfaces. Hope you still remember that. So we have this, what we call the saddle point, right? This is like a saddle in a horse. If you are riding a horse, this is something that you need to put on the top of the horse, right? So this is at the middle one here. The point here is, we call this saddle point, right? And the interesting part on this saddle point is, this is not maximum or minimum, right? But certainly it is a critical point, okay? But still critical point. So in our case, what we can find in this maximum minimum values, we can find maximum values, we can find minimum values, and we can find the saddle point. Sometimes we can find the saddle point. So at least these three will be our goals. So if we have a surface and we can distinguish all these three, then that will be sufficient to for our lecture. And how to find the saddle point? This is what we have. The second derivative test. Let me put here into the top. Okay. So to prove this, there is, I think, another additional lecture to prove it, but let me just give you first what's going on. So in calculus 1, we have the first derivative test, we have second derivative test. We have first derivative test to get to know the critical points, the same as we did here. In calculus 1, the second derivative is to look for the curve, the concavities, concave upwards, downwards, and so on. But here, the second derivative is a little bit different. So we are going to have the second derivative partials, and then we're going to put those partials inside our, what we call D. The D is actually for discriminant. So we call this D for determinant, and then put this partial x, which means this is the second derivative partial. We partially derive x, and then x, and then this is y, and then xy, or yx, they're the same, and then square, minus square. And then we have this three category. So if D is positive, and then the partial xx is positive, then this will be local minimum. Okay? And if D is positive, but the partial xx is negative, this will be local maximum. Okay? And then if D already negative, then this is going to be the saddle point. Okay. So you can imagine D is like this. Okay? You can also write D in terms of matrix if you want, because this is actually proving using matrix. So this is F pref x x x y y. Yeah, determinant, right? So you multiply this and then minus with the other one, right? Okay, how we get this determinant is actually from directional derivative, but I think I don't have time to prove that for you. So I will try to look on some other sources that maybe have. But if you want to try, the idea is, let me just give you the idea. So you have directional derivative, right? Let me write in terms of partial x, or maybe from this gradient factor, and then multiply with u, or maybe let me just write u as hk, or ab. So this will be partial x h plus partial y k. Okay. And then what happened next is we are trying to take this and then try to partially derive. Okay. So we are going to try to find this du squared. So we take another derivative from this directional derivative, and you will have, I think, quite long process there. But in conclusions, you will find some signs, negative and positive, that will going through here. Okay. This is the conclusion from this. Okay, I will try to look another resource that is, I think, have a good explanations, especially for you. Okay, maybe it's better to have a practice on how to use it rather than just giving you some notes. I think we can try to try this one. Okay. So let's say we're trying some example here. Let's say we have a function. and it's asking find all extreme values. It means that we need to find maximum, minimum, and saddle point, if it has saddle point. So the first thing we can do is take the first partial. So take partial derivative. So let me write here step by step. What we need to do is first finding the critical point. So we need to take partial x equaling to 0 and partial y also equaling to 0. So partial x, we take x as our derivative and y as a constant. So we take 4y and then minus 4x cubed equaling to 0. So we get that from here, we get that y is equal x cubed. Okay, and then for partial y, we get 4x minus 4y cubed equaling to 0. Okay. And now we need to combine these two and find the relations. So we are going to substitute this y going through here. Okay. Let me use a different color. So this will be 4x minus 4 y cubed, so x cubed, so x9, right? So x9 equal to 0. Okay, I think I can move this to the left so that I have more space. So x, or 4x, and then this is 1 minus x with power of 8, right? Wow, it's 8. So do not be intimidated. We can still try our algebra and our squared algebra especially, right? Because x with power of 8 is coming from x with power of 4 squared, right? So we can still use that as our source for solving this part. So remember a minus b, a squared minus b squared is a minus b, a plus b, right? So we can just use that. So x power of 4, okay, and then plus x power of 4, okay? So equal to 0. Okay, we have 1 minus x power of 4, which we can also factorize one more time. So we have this, we have this. And then 1 plus x power of 4 is not factorizable, right? Because it's having a positive discriminant. So we end until here, and we can decide what kind of values that suitable, right? So from this one, I think we can conclude that x should be 0, right? And x also positive, negative 1, right? So we write positive, negative 1. At least we have these 3 values from here. Another value is, I think, imaginary number, which is not going to be our case, so we can ignore the imaginary. Okay? So we can just use the real value. Okay, my suggestions when you are trying to test these functions is take the table. Okay, just make the table. So we have x 0, right? X plus minus 1. But we need to also using x to get y. Okay? So since y is x cubed, so all the negative will be still negative, and all positive still positive. So or let me write. So when x 0, y also 0, right? From here. When x is positive 1, y also positive 1, or let me write. So x is 1, x is negative 1. So for x 1 is y also 1. So for x negative 1, y is negative 1. So the same value for x and y. So put that x and y, so 0, 0, right? And then 1, 1, and negative 1, negative 1. Okay, and then the middle part you can write d. What is d? D is, you can maybe write it here. D is partial x, x, partial y, y, minus partial x, y squared, like that. Okay, since we need partial x, x, then perhaps we can try to find out that as well. So partial x, x is, so partial x is this one here. So we differentiate with respect to x. This will be negative 12, negative 12 x squared, right? And then partial y, I think very similar, but it's y. And then partial xy or yx will be the same. It will be 4, right? So the next thing is we are going to input all the numbers to this equation. So 0, 0 put into x, x, this will be 0, this will be 0. So this will be 0 for xy 0, right? And xy is 4. 4 squared but having negative, so it's negative. Right? So this will be d less than 0 or negative. And we know that from our conclusions that this is going to be the saddle point. Okay. Okay. Let's go back to this part. Okay. So perhaps let me make another column that this is this column for last one is for the partial x. Okay, so let's try the second row. X equal 1, y equal 1. So we put into the d, so partial x is negative 12x squared, which means it's negative 12 and then negative 12, so it's positive, right? So it's positive, okay? Yeah, it's positive. Then we need to know the partial x. Partial x is negative, right? So we say that this is negative, negative, okay. So positive, negative, this will be resulting in, so 1, 1 is local max. Okay. And then try another one, the last one, negative 1, negative 1. We put into the negative 12x squared and negative 12y squared, because both has squared, it's supposed to be positive, but it has negative, negative, so it's the same positive, right? So positive, and the partial xx also giving the same negative, right? Yeah, partial xx going through here, x squared, positive, but it still has this negative, so it's the same negative, right? So this also a local max. So we have two local max with one saddle point. I think if you would like to try to, yes. So if you would like to try to put this graph, I think you can try it with some software that draw the three dimension for these curves. Okay. But the typical questions for this maximum minimum value is to just to find maximum, minimum, and saddle point if you have any saddle points. Okay. I think if you have ability, yes, I think MATLAB is for sure because it's computations. I think in GeoGebra you could set the 2 dimension and you can set using 3 dimension. Yeah, I think you can set in GeoGebra. Perhaps if you have maybe later if you want to, I think you can set GeoGebra. And I think some graphers that is come along with I think if you are using Apple, I think there's one grapher that you can tweak and make it 3 dimensions as well. Or I think GeoGebra is I think the one that I think easy to use. You can check it out. Okay, another notes for this maximum minimum is we also have the absolute maximum or absolute minimum. Okay. Well, the difference is if we are looking at the absolute maximum and minimum, we need to think all the domain that is including within the functions. Okay, so we need to think on the domain and the domain, and basically to find this to find this absolute maximum or minimum. It's the same as we did before. We find the critical points, find the extreme values as we did before. But then we need to check the largest of the values, and we can set which one is the absolute one, and the other one maybe it's just a local. So it's the same. So I think not really important, as long as you understand what the difference is from absolute and the local minimum values. Okay, we can have more exercise, but I think I will keep going to finish just one more sections, and then after that maybe we can review. Okay, so the last sections within this chapter 14, so this will be the last in chapter 14, is what we call the Lagrange multipliers. So Lagrange, suppose that I think name of the person. Yeah, I think name of the person. Okay, Lagrange. So let me put here. So suppose that we have this, let's say, projected surfaces. If you remember, we have function of 2 variables that we can project to 2 dimensions, and we can set up some different level. So this constant is setting up a different level of surface, and then we have another function g that is just simply just like that, and it is touching one of this surface. So what we are going to do from this Lagrange multipliers, so let me write here. So we seek the extreme values of the function when the point write the important one with red. When point xy is restricted to lie on a level curve. In our case, the level curve G. That's our constraint. So let me write here. G xy equal some k. So with this constraint, then we are going to find, so let me write here. So to maximize this function xy subject to g, then we need to find the largest value of C, the curve, okay, the curve C of such that level curve of this fxy is equal with that C, and intersect function g. Okay. So when these two intersect, okay, this is important here. So when f and g, they both touch each other, they intersect each other, what will be the conclusion from those phenomena? That means the normal line for both f and g are identical. Okay. What is the normal line in this case? Is the gradient factor. Okay. As I mentioned, I think before, when we have a level surface, we have a normal factor that is the gradient factor. So we can say the gradient factor for this f is parallel to gradient factor of g. Or we can simply write this. And the one that is in as a multipliers here, this is the scalar multipliers which we call the Lagrange. Okay. It seems still abstract how we are going to use it. But let me give you some context. So to use this, let me write here. So how to use this Lagrange? So first we have the function f that we are meant to find the maximum and minimum values. So the case is still the same. We need to find the maximum and minimum values. So f is the one that we need to find its maximum and minimum values. Okay? And with another functions that has a constant k for it. So it is we call this constraint as a constraint with this k. And then its gradient factor is not 0. Okay. So first we are going to take the equations, this equation, Lagrange multipliers, with Lagrange multipliers, with this constraint as our evaluation, for evaluation value. So we can first either finding the relations between this gradient f and gradient g. So we can relate the x with other x, y with y, z with z, okay? And then we see how does it relate. We can also find Lagrange itself, okay? And then lastly, we can simply say what will be the either its maximum or minimum from this relations. Okay? So let me just go to give you some context here. So suppose that if, so example, so if you have functions f, okay, suppose that we are going to evaluate this, okay. So we need to find max, min values. But we do know that it has a constraint that is 3x plus 2y, let's say negative 8z equal negative 50, which means that every value x, y, z from the function f, we can restrict to this constraint. That's why at the first picture you see the graph is being touched okay, touch at some certain point that we call the we have a multipliers Lagrange. Okay. So first we can let this gradient factor equaling this other gradient factor with some multiplication of the Lagrange. So we can find first the gradient factor for each. So for f, we get 6x, 2y for z. Oh wait, it's supposed to be negative. So that I will have the same result. And the gradient for g is 3, 2, and negative 8. Okay. Now we can break down for each axis. So partial x equal Lagrange lambda gx. Okay. So 6x equal 3 lambda. Okay. And then we can go for all possible relations. So 2y, and this is 2 lambda, and a partial z. So this will be what? Or this is y equal lambda. This is x equal half lambda. Okay, just to make sure. So partial z is negative 4z and negative 8 lambda. So z is 2 lambda, right? So we get all this lambda, right? We get all this lambda, or in terms of x, y, z. And I think we can get the lambda from our constraint. So 3 input half lambda, so from the constraint value, plus 2 lambda, plus or minus 8, this is 2 lambda. This is supposed to be negative 50. So we get 3 over 2 lambda plus 2 lambda, negative 16 lambda. So what this is, I think let me just multiply by 2. So this will be negative 100. This is 4. This is 4. So 3 plus 4 is 7. 7 minus 32 is 25. Or my negative. And then lambda is 4. So it says that lambda is equal to 4. So when lambda is equal to 4, then we go back to the xyz here. That x is 2, y is 4, and z is 8. It says that within this 2, 4, 8, based on our Lagrange multipliers, this is our extreme value. So we check what kind of value that might be possible from this case. Check f 2, 4, 8. So we check f. So 3 and 2 squared plus 4 squared minus 2, 8 to the power of 2. This will be 4, 3, 12, 16. So 28, oh, it's negative 100. But is it maximum or minimum? How do we know? We can check just some other points that can be made out from this f. For example, let's say we take 0, 0, 0. What will happen with our f? It seems that it's still below that point, right? So I think it is the possible for this negative 100 is it is going to be minimum value. Okay. And to solve these Lagrange multipliers, there will be some algebra here. It's not always this case. It can be first maybe we are going to have the lambda is equal to some x, and then we are having different process, but still we take the relations between these two gradient factor f and gradient factor g. There will be some other case aside from this one. So this is if we have one constraint. There can be two constraints. If we have two constraints, I think let me just show you first, and then we can have another example. So we can have this case altogether. So this means that if we have two constraints, if we have and here is G and H. So which means that we have two Lagrange. So this is the lambda and the mean. These two Lagrange will be our multipliers. Basically, we finished the chapter, but let me give you an example, just to let you familiarize with the subject. Here's some other interesting question. Let me write here. Another example. This is still one constraint. Okay, let me just write. If we have x, y, z, let me just give you a simple function x, y, z, and then has a constraint. X squared plus 4y squared plus 16z squared equal 48. Okay, let you try to solve, or let me just write the question here. Use Lagrange multipliers. To find extreme values. So as long as you have a constraint, I think Lagrange can help you find the extra values in more direct rather than the method that we discussed before, just a maximum minimum value. Yeah, each one of them has positive and negative. For Lagrange, you need to have at least constraint to restrict your computations and find the values, the extreme values. So first, as usual, we are going to let this take the partial and take also this partial, and then we are going to equaling both of them and multiply with our Lagrange, the lambda. It's a little bit different case from the previous one. So we can start by taking the gradient factor. So partial x, this will be yz, xz, right? And then xy, yeah. Seems simple, but it's actually quite long. And then the gradient for g, this is what, 2x, and then 8y, and then 32z, all right? Okay. So far so good. And then we take partial x equal lambda gx, okay, So yz equal lambda of, and then 2x. Let me put on the left there. And then partial y. This is 8y. And for y, this will be xz. Oh, why I'm write g first. And then 8y. And then partial z. To z. Okay. Since we have all in terms x, y, z, x, y, z, x, y, z, but they have all the same common lambda, right? I think it's best to just let all these equations in terms of lambda. So lambda equal this x, y, z, and then maybe we can see some interesting pattern from those point of view. So we can take lambda is yz over 2x. Lambda is xz over 8y. And lambda is xy over 32z. Okay, so because we have all the same lambda, so all this component here that is in fractions, they are equal, right? So we can some sort of solving this equations because they are the same lambda, right? So we can take this and equal it with this, then you can cancel the z, right? And maybe we can take this with this and cancel the x, and we can have much more simplified equations. So let's take that approach. So we take yz over 2x equal xz over 8y. So we can cancel this z. And this is 4. So we have y squared. 4y squared equal x squared. Okay. Maybe just give line here just to take notes. Maybe this will be an important substitution. And then we take xz over 8y equal probably here xy over 32z. So cancel this x, and then 8, this is 4. So we get 4z squared equal y squared. So let's take notes over here. Now what will happen? The next thing is look back into our constraint. Let me just copy my constraint here. Then I think we can conclude what we need to do from here. So it seems that we can exchange all in terms of y. So x we can exchange here, z we can exchange here, so we have y squared altogether, right? Okay. So yeah. So we can exchange x squared becomes 4 squared, and 4 squared, let's just stay at 4 squared, and 16z squared is y squared, right? So 4z squared is y squared, so 16 is 4, right? So it has plus 4y squared. Okay, and then it's equal to 48. So 12y squared is equal to 48. So y squared is equal to 4. So y is having positive negative 2. But then it's not yet over because we need to try all the numbers. We need to try all the numbers. So when y, let's say this is going to be positive 2 and negative 2, then we need to take this and make out with x what will happen with x, or perhaps we can just write from this x squared here. So x squared, let me write here, x squared is 4 y squared, right? Y squared is 4, so this x squared is 16. So we have 4 and negative 4. And for z squared, or 4z squared is 4. So z squared is 1. So this will be 1 and negative 1. So what will happen? We are going to have some combination of these numbers that we need to try on. Okay, so let me make it small first because I need to make some table. Resize a bit over there. So we have x, y, z. Let's say we have 4, 2, 1, negative 4, 2, 1, 4, negative 2, 1, and then 4, 2, negative 1, and then negative 4, negative 2, 1, 4, negative 2, negative 1, negative 4, 2, negative 1, negative 4, negative 2, negative 1. I think 1, 2, 3, 4, 5, 6, 7, yeah, 8. Should be 8. This is 2 cube, right? 2 cube, 8, right? Okay, 8 variations. And then this will be f, x, y, z. What is x, y, z, right? Just x, y, z. So we can just multiply, and it all will be the equal with value of 8, right? Which the other, if you have one negative, it will be negative, like this one. So this one negative 8, negative 8, negative 8, and negative 8. So the other one will be positive. So 8 will be max values, and negative 8 will be minimum values. Yeah. So you get the extreme values by these numbers. So it depends on the function, depends on the case. Sometimes you have like a lot of numbers to try. Sometimes you have just maybe just a single point that you need to try. But you need to figure out it, even like from the previous example, from those points, from those numbers, is it maximum or minimum? You need to try the function. Like you can try some simple numbers, whether it's possible to have maybe another larger value or smallest value. Okay, the rest I think we can have exercise and practice. Okay. So chapter 14 finished. Chapter 14 finished. Okay. I will try to list some interesting questions for you. I mean, just to try to familiarize with the method. Okay. And perhaps if I have time, maybe I will add some additional content just for exercise, just to help you, giving you some hints or clues. Yeah. So the calculus 2, the main content actually is started this one and the next sections, the next chapter 15. So 14, 15 is actually like the main dishes on the lecture. So the previous one is just like a appetizer. So this is the main dishes. Okay, I think I'll just stop until here. Any questions? Don't forget to check your Moodles. I already scheduled probably, I think this weekend. This weekend. You can try to look your Moodle, and I will put the link for the online quizzes. Hopefully you can get good score from the online. You can use calculators, anything, and try to work it individually. Okay, if there's no questions, then I will the one that give you the question. Okay, as usual,